There's no one-size-fits-all approach when it comes to building RAG systems. It's highly dependent on your use case, and if you choose the wrong pattern to start, you're setting yourself up to fail. The key element here is you need to strike the right balance between model intelligence versus speed and cost. Think about it. A customer-facing chatbot needs lightning-fast responses, otherwise you've lost your customer. So you can't have a frontier model like Claude Sonnet thinking for 5 minutes before it comes up with an answer. Whereas a RAG agent deployed in a legal department absolutely prioritizes accuracy over speed. And if you take a fully local RAG system, for example, here you're massively constrained by resources. So you need to design your RAG system around the models you can actually afford to run in-house. This is the main reason why there are hundreds of RAG strategies and tactics out there. And I've distilled them down to 9 key RAG design patterns that cover all use cases, and that's what we'll be going through today. We'll be starting with the most basic, which is naive RAG, and work our way up to the state-of-the-art multi-agent RAG systems. And this isn't just theory. Today I'll be showing you how this can be implemented in n8n to give you the knowledge you need for your RAG project to succeed. Let's get into it. The models you pick for your RAG system will heavily influence how you design everything else. And the reason for this is, generally speaking, the larger the LLM is, the more parameters it has, the higher the quality responses you're going to get out of it. This is because larger models are generally better at instruction following, tool calling, complex reasoning, and context handling. So by and large, you do get better responses out of larger models compared to smaller models. And what I've found is small language models from, let's say, 1 to 10 billion parameters can't usually reliably call tools, and in a lot of cases can only handle basic instruction following. But then there's a steep rise after, let's say, the 15 billion parameter mark, where the model's abilities around tool calling and reasoning and context handling improve, all the way up then to the main frontier models like Claude Sonnet and GPT-5. That's why I think for RAG systems, there's somewhat of a sweet spot in between these small and frontier models. A model like GPT-OSS 120 billion, for example, really is highly capable and nowhere near as expensive as the likes of Claude Sonnet or GPT-5. But the crucial detail here is even small language models of 15 to 20 billion parameters can outperform large language models if they have high quality retrieval. So it's all down to your RAG system design. If you can inject the right content into context into a small language model, it will always produce a better answer than a large language model that doesn't have the information to base an answer off. Before we get into the design patterns, let's look at 4 RAG use cases and focus on the different priorities that will dictate the system design. First up, we have a customer-facing RAG chatbot. So you can imagine that this is embedded on, let's say, an e-commerce website where customers can chat and ask questions about the product catalog or delivery information. A key priority of a customer-facing chatbot is speed. It has to be fast. And that priority will dictate which model you use. So you're going to need to use something like Gemini 2.5 Flash, which is a smaller model that'll give you much faster responses. And as these models are cheaper to run, your bill is going to be lower, which is a good thing. But because this is a public-facing chatbot, this will be deployed at scale. You could have thousands of customers asking questions of it. So you're also constrained by that too. You can't have frontier models that cost $15 per million output tokens. So these constraints, these priorities dictate the system design. And as a result then, you'll likely use a mixture of agentic and non-agentic RAG, which I'll be going through in a few minutes. You'll need guardrails because you don't want this chatbot chatting about anything. It needs to be highly specific and highly specialized on, let's say, an e-commerce catalog. You'll most likely need query routing so that you can route the different types of questions to the right tools. I'll explain all of these in a few minutes when we go through the design patterns. And the key pattern you would likely use here is the verify answer pattern, because you want to make sure that what you're telling the customer is actually true and is grounded in the retrieved data from your systems. In other words, you're better off not saying anything as opposed to saying something false. Next up, we have the idea of an AI assistant or co-pilot, like the AI agent deployed in a legal department. So here, accuracy is absolutely crucial, particularly if you're dealing with complex documents. So with accuracy being the guiding light in this project, speed is going to be reduced because you will want complex reasoning over the documents. You may need iterative and recursive retrieval. And if you're using more expensive models and larger context windows, that's all going to come at a greater cost. So it will be more expensive per user, but because this isn't public facing, you'll likely have a smaller user base, so the overall cost won't be too high. So this type of system could be deployed in lots of different ways. So you could have an MCP trigger node in n8n, and then if Claude Desktop is deployed within a business, they can simply add it as a tool and then chat to their documentation that way. Or it could be deployed in something like OpenWebUI, or this could be a Slack agent or a Microsoft Teams agent. So that way you don't need to deploy software to employees in a business. The types of techniques you would likely need here include Agentic RAG, multi-agent RAG, hybrid RAG, and that verify answer pattern as well. We'll be deep diving on all of these shortly. Another use case is an AI automation with RAG embedded within it. This is an agentic blogging system I created a few months ago. And within this sequential flow, we have an agentic RAG, which retrieves information from a knowledge base, and all of that feeds into article outlines and article generations, which then goes through a deterministic pattern to build out an article to be published on WordPress. So it's just another RAG use case where there are again different priorities. So this type of automation will be running in the background. So speed is not a problem. The key thing is it's resilient. So you can apply larger models with reasoning. So we have agentic RAG and non-agentic RAG here in a deterministic flow, and a lot of prompt chaining going on as well. And finally, onto our fully local RAG system. Here your model selection is highly limited based on the internal hardware that's available to run these models. So with a $3,000 graphics card, you may only be able to run a 20 billion parameter model. And then that massively influences the design of your system. So while there is an initial capital cost up front, the actual cost per user is quite low over the long term. And how fast the model inference is really depends on the graphics cards that you have in play. These types of solutions could be deployed again using the likes of OpenWebUI, because you want to keep everything local. I put days of work into pulling this video together, so if you're finding value in it, I really appreciate if you give the video a like and subscribe to our channel for more deep AI and n8n content. Now that you have an appreciation for the different types of RAG use cases, let's dive into our deterministic RAG system designs. First up, naive RAG. And naive RAG is the most basic way of running a RAG system. Essentially, you have a message that comes in, it goes straight to a vector store to retrieve relevant results, which goes straight to an LLM to generate a response, and that's outputted to the user. So it's ultra fast, but ultra basic. And this is how it looks in n8n. So chat trigger, straight into Supabase, aggregate all of the chunks that we get back from the vector store, and straight into an LLM call. Now I have this hooked up to a large vector store. So my documents table here has 215,000 chunks. And here I'm going to demonstrate the exact problem with naive RAG. So I'm going to ask this question, how to change the power levels on my GE Advantium oven. So here I ingested 10,000 product manuals of kitchen appliances. And if you want to see how we did this, check out our RAG at Scale series on our channel, which includes these two videos. I'll leave links for these in the description below. So if we ask this question, you'll see that we quickly get chunks from the vector store, quickly get an answer, the answer being, sorry, I don't know. And the reason for that is that the chunks that we got back from the vector store are not relevant. And you can see that the chunks are related to a different GE model. There's a cafe model, it seems to be here. Again, a cafe model. So it has returned chunks that are related to power levels of an oven, but it's the wrong model. And within our system prompt, we are being ultra specific. The LLM needs to analyze the retrieved chunks to determine if they're relevant, and if they are, base the answer off those chunks. If they're not, just say, sorry, I don't know. And that in a nutshell is the limitation of naive RAG. It's a single pass through to generate an answer, even though that query could be quite conversational, with lots of stop words and irrelevant words that are going to negatively impact the quality of the embedding that's sent into the vector store to find the nearest matches. But obviously the benefit of this approach is simplicity and speed. End to end, this took 2.5 seconds and included a vector search and an LLM inference. So highly efficient, if a little bit blunt. So as a result of these shortcomings, a lot of techniques have been invented around the idea of transforming the original user's query. So in our next design pattern, we implement a lot of these query transformation techniques just to give you an idea of how they all work together. If you'd like to get access to the 9 different RAG design patterns that I discussed in today's video, then check out the link in the description to our community, the AI Automators, where you can join hundreds of fellow builders all looking to create production-grade RAG applications. If you're serious about building AI agents, this is the place to be. So our second pattern is a deterministic RAG flow with query transformation and this verify answer pattern that I talked about previously. So here there's no tool calling, so we need to decompose the entire retrieval flow. This type of flow would work with most LLMs from 5 billion parameters up to trillions of parameters. And here I'll be demonstrating how when a user's question comes in, we first decompose that query because there might be multiple asks within that question. And then for each of those sub-queries, we expand upon it. So we find different angles to actually search the knowledge base for that question. We then carry out multiple vector searches and then use a technique called RAG fusion or multi-query RAG, where we actually fuse those result sets together and carry out re-ranking. This then gives us the top results from the much larger candidate set that was retrieved. That's then sent to the LLM to generate an answer, and then our verify answer call checks the answer against the retrieved context from this stage to make sure that it's actually accurate. If it is, it outputs it to the user. If it's not, it goes back to the LLM to generate an updated answer with the guidance on where it went wrong. So let's see it in action. And for this, unlike our previous question, let's ask a multifaceted question. How to change the power levels on my GE Abacus mixer? Now, an Abacus mixer doesn't exist. And how do I clean it? So let's ask it here, and off it goes. Now I've tied in chat history as well, so that we can retrieve the chat history, and there is nothing yet because I've refreshed the session. We've got back a quick answer, which is great, but let's just look at what happened. So firstly, we go to this query intent and decomposition step. And what we're doing here is we're breaking down this question into multiple sub-queries or sub-questions. And on the right-hand side here, you can see, number one, it's outputting that it needs retrieval, which is crucial. And number two, it's outputting the sub-queries. The first one is how to change the power levels on a GE Abacus mixer, and the second is how to clean it. It then goes through this retrieval gate, because if someone is just asking a question like, hi, how are you? You don't need to go to a vector store. You can simply just output an answer up here, which is ideal for small talk, as you can see. But because this question does require retrieval, it goes through this gate, and we then go to our query rewriting and expansion call. And here we're transforming the original query, or the subquery in this case, by adding synonyms, related terms, different phrasing, trying to come at it from different angles to get different chunks back from the vector store for a more rounded candidate set. So within this node, on the left you can see we have how to change the power levels, how to clean it, and on the right you can see the different rewritten queries to come at the search from different angles. And the other thing we're doing is we're asking the LLM to classify the incoming message based off a product category, because this will help us narrow the search within the vector store. We have 200,000 chunks, so ideally we should be able to narrow this with the metadata filter, and that way we'll have a much more focused search for these terms to be able to get back the right chunks. And as you can see here, it's saying that it's unsure what product category this product fits into. So a lot of this is in the system prompting. So here I'm saying the only valid options are ovens, washing machines, toasters, and unsure. But you could list all of your metadata values here. Okay, so from here then, we're splitting out again. And here I have a simple code node that checks to see, are we unsure of any of the categories? Because if we are unsure, we should just get straight back to the user and ask for clarification. And this brings us to this if node. And because we are unsure of what this Abacus mixer is, we come down to a query clarification call. And here we've identified an ambiguous or an underspecified query, and we're going to ask the user to actually clarify. And it's output of the response. To help me provide the most accurate information, please clarify what type of mixer you're referring to. And that's effectively then what's output to the user. And then we've updated the chat history. So you can see then within the chat messages, what the LLM generated is outputted to the user. Are you asking about a food mixer or an audio mixer? So this is a great way to ask clarifying questions of the user to help you refine your search within the vector store based off metadata filters. So let's just follow up and say, sorry, I meant the GE Advantium oven. Okay, and that's working its way back through the process. And now it has identified the actual product category. So let's now take it up here. So we've now passed this gate and it's true. And now we're into a technique called query routing. So here we're going to direct the queries to the most appropriate metadata filter in this case. So the switch has ovens, washing machines, and toasters. So here we're coming up through the ovens path, which sets the metadata filter. So we're setting the product category as oven. And when we go to the vector search then, we're actually passing that product category as oven, along with the prompt. And because we've expanded out the prompts previously, this is just one of 5 searches we're going to have on this vector store. So this one is GE Advantium oven, change power levels. But if we look back here at the query rewriting and expansion, you can see that we have multiple queries that we're going to search the vector store off. How to change power levels, how to adjust cooking power, how to clean the oven, cleaning instructions, maintenance guides. So all of these keywords are going to be sent into the vector store to get back a diverse collection of chunks. So you can see this is already way better than Naive RAG. Naive RAG sent in a really long rambling query by the user, whereas here, not only is the query written, it's also expanded into multiple queries to cover a wider range. As a result, we end up with 50 items coming back across all of the different queries, because we're getting 10 chunks per search. We then go through the process of RAG fusion. So with these multiple queries, we're going to end up with a lot of duplicate results. So we need a way of deduplicating and fusing the results together into an ordered list. And that's what this reciprocal rank fusion step does. So essentially, if one chunk appears in multiple lists, it'll rank higher than a chunk that only appears in one of the lists. The lists being the 5 queries that we ran against the vector store. So of the 50 chunks that we retrieved from the vector store, there are only 20 unique chunks, and they are now ordered based off that fusion process. But that fusion process is pretty crude, as I just described, so we also carry out a re-ranking stage. And here we're using Cohere 3.5. You could use a local re-ranking model if you wanted. But what re-ranking does is it sends in the user's question, as well as the 20 items in this case, into a cross-encoder model, which is similar to a basic LLM. And what we're doing is we're asking it to take the 20 items and only return the 10 most relevant ones in order. And that's what it has done there. So here we're just setting those up then to send into the LLM, which is what we do to generate the answer. And you can see we're sending in the user's question, the chat history, as well as the top 10 chunks ordered by relevance from the re-ranker. And that's helping to produce this quite accurate answer. And finally, we go through our verify answer pattern with the feedback loop. So what we do is we send in that answer that was just generated, along with the user's question, along with the chunks that we got back from the vector store, and we're asking the LLM to make a judgment on, is this answer fully grounded in the context that was retrieved? Are there any contradictions? Are there any unsupported claims? And from there then there's a decision. If it's grounded, we can just output the answer to the user. If it's not grounded, then we can go back to the LLM and pass the feedback to say, you need to make these changes. And it works its way back through the process. It only does this a couple of times because you don't want to get caught in an infinite loop. And finally, it outputs a response to the user and updates the memory. So that's what the end-to-end process looks like for a deterministic RAG flow with query transformation and the verify answer pattern. And what's brilliant about this is a small language model can actually run this. There's no tool calling. Any of the really complex system prompts have been broken into multiple calls to LLMs. And time-wise, if we look at the logs here, you can see that end-to-end, this took 30 seconds to retrieve quite an accurate answer. And I've baked a lot of query transformation strategies in here, so you could probably strip some of these out and actually get that even faster. And it is worth calling out that this is what production RAG systems look like. It's highly focused LLM calls. It's super fast vector searches with chunks injected into context to get ultra fast answers. And if you look through the logs here, the real bottlenecks are actually in the answer verify pattern, which takes 9 seconds, because there's a bit of reasoning required over the data. It's absolutely possible to use agents within this type of flow, so you can end up with the hybrid, agentic, yet deterministic workflow. Our third strategy is deterministic RAG using iterative retrieval. And it's a similar flow to before, with the exception that after the re-ranking stage, before generating the answer, we have an LLM call that analyzes the results, and it determines whether we actually need to retrieve more from the vector store because the quality of results isn't good enough to formulate an answer. And then you can keep a count on the number of iterations that you progress through to again avoid an infinite loop, similar to the answer verify pattern. And once you're happy that you've retrieved enough or you've hit the limit, you can then go to an LLM to generate a response to the user. I haven't mapped this one out on n8n, but essentially you'll be injecting the LLM call here. This would be your analyze results call, and then you would have an if node. That if node is should you retrieve more? And if we should retrieve more, then we need a counter to make sure that we're not stuck in a loop. So should we stop? We'll drop that in there. And if we should stop, then generate the answer. If we shouldn't stop, if we can go again, then we go back to the vector store. And we pass in the new queries that were generated from this analyze results node. And if the retrieve more says we're done, we can also just connect that up to the generate answer. So that's the type of implementation you would need. Of course, this would also increase the time it takes to generate a response. So again, back to the use cases, if you really need high quality responses, this is a good pattern to use. Another variation on this deterministic flow is adaptive retrieval as opposed to iterative retrieval. I really like this design pattern, and I already have some of this implemented in what I've shown you so far. So with adaptive retrieval, what we're doing is we have a query classifier. So you saw it earlier where I said, should I retrieve yes or no? That's essentially this piece here. So if the query classifier runs and it determines that no retrieval is required, you can simply just use what's in the LLM's training data, then you just generate a simple response. Whereas if retrieval is required, it then defines it as a single step retrieval or multi-step. If it's a single stage retrieval, you just send in the single query or an expanded query and get your results and output the response. Whereas if it's a multi-stage retrieval, you end up again in a kind of a recursive pattern. So you send in your first query into the vector store, you get your results and re-rank them, and then based off the retrieval strategy, if it's multi-step, you go to an analyze results node, and it then analyzes to see, is retrieval complete? Has it hit enough steps? Because it's a complex multi-step query, have you done enough research? Have you done enough digging? And if you haven't, it generates more queries, which goes back to the vector store, and it cycles through until it's complete and an answer is generated. So this is kind of similar to how GPT-5 operates its router. If you interact with ChatGPT and if you ask a very simple question, then behind the scenes, OpenAI is sending that really simple question to a small model to generate an answer. Whereas if it's a moderately complex question, it'll go to a decent model, but probably not a frontier model. Whereas if it's a really complex question, it's going to hit its largest model, it's going to use reasoning, and it'll take a couple of minutes to generate a response. So that's essentially this pattern, adaptive retrieval. And within n8n, we have some of this already covered. So the query intent is essentially your query classifier. And the retrieval decision here, first determine if this query requires retrieval from the knowledge base, select no retrieval or needs retrieval. Instead, you would have no retrieval, single step retrieval, or multi-step retrieval. And then if no retrieval, you just come back to the fallback message and output to the user. And then whereas down here then, again, you would just split at this mark and you would have an if node, which is your retrieval strategy. And let's say if the retrieval strategy is single step, which is the top leg here, then you just generate your answer and off you go. Whereas if it's multi-step, then you would come back down here. You have an analyze results. You decide whether you need to retrieve more. Have you gone deep enough? If you have, should you stop? Because you don't want to get caught in a loop. So exactly the same idea. So you would tie that one there. You don't need to retrieve more. Or if you do, and you're happy to continue, that will go back to the vector store with the updated queries. So again, the same type of recursive iteration and looping, but now it's based off a retrieval strategy based off a query classifier. So you can see a lot of these RAG strategies and tactics are kind of variations of each other. Adaptive retrieval is similar to iterative retrieval. So that's our first 4 RAG system designs covered. And just to reiterate that while all of these can run on small language models, they also can run on large language models. You can have AI agents buried within flows, deterministic flows like this. And the beauty of a deterministic workflow is that it's highly reliable. It will do the same thing every single time it runs, which is totally different to the idea of AI agents. Because with AI agents, through a system prompt, you're trying to persuade it to do what you want. Whereas with the deterministic workflow, it has to do what you want because you've designed it that way. So this hybrid approach of a deterministic yet agentic workflow is highly powerful in a production RAG setting. Now that you've seen deterministic RAG system designs, let's look at some agentic RAG patterns. And let's start off with standard agentic RAG and hybrid RAG. And on the face of it, your standard agentic RAG is quite simple. It's an AI agent that receives a message from a user. It has various tools that it can call to help retrieve context to generate a response. So here it could have a vector search tool, a database search tool, a web search tool, and you can load in quite a complex system prompt in to try to convince it to do what you want to do. You could give it a standard operating procedure, you could use prompt engineering techniques to really urge the agent to follow the right series of steps, if that's the approach you want to take. Based off all of that, it can then output a response to the user. And this is what it looks like in n8n. This is probably pretty familiar. Standard chat message, standard AI agent. It has a vector search tool with an embedded model hooked up. And then agents also have memory. So here we've just assigned a simple memory, but you could have different types of memory like Postgres or Zep. And then we have an AI model hooked up. And as I mentioned earlier, small language models under 10 billion parameters can struggle with reliable tool calling. So your selection of model here is important. I've hooked up a frontier model, Claude Sonnet 4.5. So let's ask the same question, how to change the power levels on a GE Abacus mixer. And the beauty of these agents is that it can hit a vector store numerous times with different variations of a query. So this is the same as query rewriting, for example, or query decomposition. It can break up the query and hit the vector store numerous times. Sometimes it just does that off its own bat, other times you need to prompt it in the system prompt, but because it has this function calling loop, it can do it numerous times. And as you can see, it's saying it can't find any information about the Abacus mixer because it doesn't exist. So I'll say, sorry, I meant the GE Advantium oven, and because there's memory attached to this agent, similar to the way we were updating the chat history in the previous flow, it's able to fill in the blanks and figure out that it needs to retrieve cleaning information as well as how to change the power levels of the oven. So it's hit the vector store 6 times already and has now outputted an answer, which looks quite good. And if we have a look at the vector search, you can see the different queries that it passed. So Advantium oven power levels, cleaning instructions, settings, adjustments, cooking, interior, exterior, care, maintenance. So it's just passing lots of different keywords to try to get a broad range of candidate chunks that it can actually feed into its context to output an accurate answer. And this is why frontier models are great. There was no need for any of the query transformation steps that I showed you in the previous design patterns, because it's such a smart model, it can figure that out. Claude 4.5 Sonnet is probably one of the best models out there, and one of the most expensive. So by way of a comparison, let's try this out on the GPT OSS 20 billion model. This is an order of magnitude smaller than 4.5 Sonnet. So I've set the GPT OSS Safeguard 20 billion model there, and let's ask the same question. So it has hit the vector search, so it is able to actually call tools, which is great. It is getting a decent answer. I'm sorry, I don't have the specific instructions. Let's ask it again, just to see, do we get the same response? We probably will, actually, it's in memory. No, we didn't, actually. We are getting some instructions on how to change the power levels on a GE Abacus mixer, which doesn't exist. So I got it right the first time, but when I asked the same question again, it didn't get it right. Let's reset the chat session and we'll just try that question again. So it's gone to the vector store numerous times. Again, it's a good answer. It doesn't actually exist. But just when I repeated the question, it must have thought that I really wanted an answer, even though it wasn't in context. Let me try that with Sonnet 4.5. I'll ask it a couple of times. Okay, so we get our apologies, doesn't exist. Please clarify. So let's ask this exact same question again. Yeah, and it still doesn't have the information. So I think that's kind of a good example of smaller models. They are less reliable than the larger, more intelligent models. For some reason, GPT OSS 20 billion thought it was okay to fabricate the information because I asked the question twice. whereas a larger model is smart enough to realize it still doesn't exist, it's still not in context. And that is why benchmarks exist. It is a quantitative mechanism to compare these models, even though by all accounts they are being gamed by the various model providers. But either way, you can see how Agentic RAG works, and the idea of multiple tool calls with different queries, so a lot of the query transformation is wrapped up in the reasoning of the model itself. Hybrid RAG is essentially the same thing. The only difference is you don't just have semantic search attached, you also have different representations of data within different systems. So here we have a database search tool. So this is a Postgres database, and you would require the Hybrid RAG agent to write a SQL query to actually fetch results from that knowledge base. As for this one, this is a graph search tool using Neo4j. So the Hybrid RAG agent would need to write a cipher query to be able to traverse the knowledge graph and return the results. So that's what Hybrid RAG is, retrieval from different types of data stores, such as vector, graph, or database. If you want more information on database search tool calling, Alan has a video on our channel called Agentic Databases, which is well worth a watch. And on the graph search, I just released a video on graph agents a couple of weeks ago, where I show how to set up Neo4j and actually configure your n8n agent to traverse through a custom knowledge graph that you can create. I'll leave links for these in the description below. So on to pattern 7, which is our multi-agent RAG system using sub-agents. You've probably seen a lot of this on YouTube with n8n videos. But here, instead of tool calls which are outbound external to different services, we're calling another agent, and that agent has its own system prompt and has its own context window. And this is a really good pattern because if we go back up to our Agentic RAG setup, you could have quite a complex system prompt for this AI agent. And if you have a really smart model like 4.5 Sonnet, it will by and large follow that prompt, particularly if you enable reasoning and it can think about it a bit. But at the same time, there is a limit to the complexity of system instructions that a model can actually follow. At a certain point, you need to break that apart into different specialized agents. And that's what this multi-agent RAG setup is. So here we can simplify the system prompt of our agent and farm out some of those responsibilities to sub-agents. So if we're looking at our database example, you could have a database sub-agent who has numerous SQL tool calls. And sometimes these SQL queries can be incredibly complicated. And with few shot prompting, all of that buried in a system prompt at the AI agent level would totally overwhelm it, and it wouldn't know where to focus to actually follow the correct set of instructions. So instead, we can dedicate a sub-agent just for the database queries, and we can give it all of the examples that it needs to effectively trigger these SQL tools. So that's a good example of simplifying the system prompts. Another benefit of this approach is protecting the context window. I released this video 3 weeks ago on a technique called context expansion. And what this means is you have the ability to load up an entire document into context if the query actually requires it. So let's say a question came in asking, can you summarize this entire document? And it provides a link to a document. For an LLM to summarize it, you can't really use RAG, because RAG will only give you segments of the document. If you need to summarize it, you need visibility of the entire document, which means you need to load the entire document into context. The problem with that is there is a limited amount of space in context. So if your main agent has, let's say, 5 steps in a procedure to follow to output a result, and one of those steps is to actually load an entire document, then once it does that, it might get confused because it doesn't know where to focus within the context itself. And it might end up messing up steps 3, 4, and 5 as a result. So with this pattern, you can offload the context overhead to a sub-agent. This document researcher, its only job is to load a document, summarize it, and send back the summary. And at that point, it can just forget it. So the agent will never see the full document. It'll only get the summary to continue to steps 3, 4, and 5. So there are lots of benefits to having a multi-agent setup with sub-agents. And this is what it would look like in n8n, where you have your Agentic RAG, and as tools then you have your sub-agents. And this is pretty easy. You just click on the plus and just type in agent, and you have this AI agent tool. And then you can just attach your model, attach memory if you need to, and attach the various tools. So my database sub-agent, you could have lots of different kind of SQL, Postgres tools with different prompting. The document researcher could just have a fetch full document tool, and that could be a Google Drive, that could be a Google Cloud bucket, or it could even be a Postgres tool that fetches all of the chunks based off a document ID. So then when this agent is called, it can trigger the sub-agent to carry out the work, provide the responses, and it can continue on its merry way to generate an answer to the user. So it's a pretty good pattern. I would have one word of warning though, which is that you do need to be highly specific around the roles and responsibilities within this type of structure. A few months ago, I created a vast multi-agent system called HAL 9001, as you can see here. And within this setup, I had 25 sub-agents for a main HAL orchestrator agent. And it was incredibly unwieldy because each of the agents needs to be tightly configured, the tools need to be tightly defined, otherwise it becomes an unreliable mess trying to actually get responses that are anyway accurate. It can get lost in conversation between the various agents. So you do need to be quite conservative when you're actually building out multi-agent RAG systems. I would honestly start with just a single sub-agent, get that working really well, then add another sub-agent and regression test the whole thing and continue on. Conservative is best, I think, with this one. Another pattern for multi-agent RAG is with sequential chaining. So this is more aligned to the deterministic workflows that I showed earlier. Here you would have a chat input. It would go to one agent who would produce a response after interrogating various tools, and that would then feed another agent to carry out another action to produce a response to the user. So it is more sequential. Again, you can have simpler prompts. Each agent can be more specialized. So for example, you can have a research agent, which carries out research based off various tools, and then that goes to a writer agent who creates a blog post, and that goes to a publication agent who publishes it to social media or to WordPress. And this doesn't need to be a chat trigger. This is more aligned to the AI RAG automation that I talked about earlier in the use cases section. This is our Agentic RAG blogging system. And here the actual trigger is NoCodeDB, or it runs on a schedule. NoCodeDB is an open source Airtable equivalent. And depending on what action was triggered, if the blog article is ready for outlining, it goes up to this agentic researcher. And this is a RAG researcher that has access to various tools, like a semantic search database, a structured SQL list based off a table. We have deep research with Perplexity and a deep search with Gina. And this agentic researcher is part of a sequential chain, because once the outline is created, it can then go and actually generate the article. Now there is human in the loop built in as well, but from here then it's a full chain of AI nodes and different features to actually build out the article, generating images or searching for stock images, writing and uploading the article to WordPress. Here we're using another AI agent, uploading the featured image, writing the social posts, updating the publication system in NoCodeDB. So you can see the benefit of a fully sequentially chained multi-agent system. And it can be a hybrid as well. These don't need to be agents. These could be kind of one-off LLM calls that generate text responses or JSON outputs that feeds the next step in an automation. And finally, the last pattern for today is a little bit of a mix of everything. It's a multi-agent RAG system with routing and sequential chaining. So for example, if it's a very simple question, we can just drop it into the simple response and send it back to the user. Whereas if it's a question about writing, it can go to this agent. About research, it can go to that agent. And this is a great way of speeding up inference of an agent, because if you go to a multi-agent setup with sub-agents, there's a lot of supervision and orchestration of the responses. Whereas here you can just route the query directly to the agent who actually can answer the question. And you still have separation of concerns. You still have specialized agents with their simpler system prompts and specialized tools to carry out the tasks. So this is how it looks in n8n. Again, standard chat trigger. We have our query classifier and router. Off the back of that, then we get a structured output that we can then funnel the user down a path. So if it's a simple question, we can then just generate a friendly response and output the answer. If it's a question about publishing a piece of content, for example, it could go to the publication agent. And you can mix and match the sequential side of it too. If it's a task about researching and drafting a piece of text, then it could go to a research and writing agent that are then linked in a standard sequential chain, and then you get the output response. So it's quite simplistic here, but you get the design pattern that we're trying to achieve, which is this idea of query routing in a multi-agent setup. There are other patterns that I didn't dive into on this video. Self-RAG, for example, uses reflection tokens to determine the quality of retrieval and whether it needs to go and retrieve again. So it's kind of a variation of iterative retrieval. Corrective RAG is an approach that uses web search as a fallback if the content can't be found in the knowledge base. Guardrails is a way of protecting your system from prompt injection attacks or PII leakage. Human in the loop is a way of escalating and bringing in a human to actually interact with the flow. And this can be quite useful for the likes of these RAG automations as opposed to the chat interfaces. Human handoff is another variation of this, where the actual chat message is directed to a real-life human when the agent can't actually answer the question of the user. That obviously works great if you have a support team on standby waiting for messages to come in. Multi-step flows is another pattern, which is more aligned to traditional conversational chat flows, where questions are asked in sequence, and then the answers feed the next stage of the sequence. And the key challenge there in a conversational interface is keeping things on track, because if people break off mid-flow, then how do you know what they're now talking about because they were in the tunnel completing a particular task within the actual chatbot? Context expansion is the technique I discussed in this video, Next Level RAG, where you grab neighboring chunks, document sections, subsections, or even the full document itself. And then deep RAG is an emerging trend around this idea of deep agents and having a retrieval planning system and executing that plan over a longer time horizon than you typically would find in a conversational chatbot, for example. There's one technique I didn't discuss in this video, and not enough people talk about it, which is lexical keyword search, dynamic hybrid search. If you want to learn more about that, then click on this thumbnail here.